So good morning, everybody. Thank you very much for joining this session. My name is Enrico. My colleague on stage is Abhi. We both work at CERN. And today we will walk you through some recent work that we did around improving business continuity for the Ceph infrastructure that we operate at CERN. So the nice picture that you see in the background is actually representing the particle collider that we operate and we built at CERN in Geneva. The white ring is the collider itself. This has a 27-kilometer diameter. It's actually built underground. It's 100 meters underground. It's inside a tunnel. This is a picture from the tunnel itself. The particle accelerator is actually in this blue pipe that you see on the left-hand side of the picture. And there we have basically superconducting magnets. We accelerate particles to almost the speed of light, and we steer these two beams that we have flying in opposite directions, and into very precise points of the LHC facility, we collide the two beams to provoke particle collisions. Colliding particles at precise points is relevant because at those points you have what we call the detectors. We have 4 detectors along the LHC. This is a picture of the CMS-1. And you can think about this huge, very specialized and expensive thing as a gigantic camera that takes very special pictures like this one. This is actually a picture that we produced by reconstructing a collision of 2 particles, and this actually just happened few minutes after the LHC restarted its operation in July last year. So besides all the physics facilities, we also do quite some IT. We have 2 computing centers. The main one is this one on the bottom part of the picture. It's an historical one. I think it was built like in the late 60s or early 70s. It's on the main site. We are actually building a second one, which is 5 kilometers apart, and it's expected to be delivered and operational by the end of the year. So just a brief introduction about the 2 of us. I'm Enrico. I have a PhD in computer networks. I joined CERN in 2017, but I was exposed to CERN operations only later on, since 2020.
I'm Abhi. I've joined CERN since 2 years ago, and then I've been in Ceph operations since the last year. I've been involved with the Ceph project for a few years, though.
Yeah, and we both work in the IT department, and more specifically in the storage group. So now the pictures are over. We go to boring tables. This is a summary of the clusters that we run at CERN. We have 16 production clusters. We use Ceph in every single possible form. We have block file storage and object storage. What we typically try to do is to use one cluster and let it do one thing only, which means if a cluster delivers RBD, it does RBD only, and we do not collocate CephFS or Rados gateways onto the same cluster. If you sum up the size column, this is roughly 65 petabytes. We are actually procuring new hardware for the new computing center, so I hope that for Cephalocon next year we will be beyond the 100 petabytes bar. Most of our capacity is on spinning disks. We have very little capacity on full flash storage, though we use flash for the RocksDBs of the OSDs and for the metadata pool of CephFS. And Ceph is actually one of the casting stones of the IT infrastructure at CERN. We use it for many things. The first and foremost important integration is the one that we have with OpenStack. We have 450,000 CPU cores in OpenStack, and Ceph is basically the storage that backs all of that. This is also very practical for users because it comes as a sort of an infrastructure as a service package. So users just go to the OpenStack web interface or to the command line, they spawn a VM, they get some storage, then I touch it to the VM. It's all very practical and self-managed for them. Over the last years, we see also more and more usage from Kubernetes and OpenShift clusters, so container-based workloads. These are mostly CephFS oriented, and then we use it for many other things. We use it for monitoring, for analytic tools, more traditional document and web hosting. We also use Ceph internally to the storage group to virtualize some other types of storage, like we have NFS and AFS, which are fully virtualized on OpenStack VMs, and the storage is actually Ceph RBDs. So the purpose of this talk is basically to walk you through and share the experience that we have collected by testing many different Ceph features, and actually not only Ceph features, that are interesting for us in the context of business continuity and disaster recovery. Disaster recovery was not part of the original title. It's actually something we are very much working on these days because it's perceived as a priority for the whole organization. So you will learn some things about DR as well. So this is the outline. We will go through many things. Some of those we will just hint at them. Some are even moved into some backup slides in case you're interested. So there are many things that we can discuss. Upfront, we can guarantee two things. We will speak very fast and you will likely be late for lunch. So let's start with block storage. I think the first deployment at Ceph for RBDs dates 2013. I was not there yet. Dan van der Ster, who is in the audience, was there. He initiated the whole thing. Thanks a lot for being here and for not putting any pressure on us delivering this talk. So he was the person that brought Ceph at CERN, one cluster, initially RBD. It was a proof of concept. It scaled out very well in terms of capacity. We went through many different hardware generations. It has demonstrated to be very reliable and very stable over the years, up to one day in 2020. Dan had a very bad day that day, where we basically hit a bug in the LZ4 compression library that brought to the corruption of OSD maps. OSD were crashing, PGs went inactive, all IOs were blocked, and this was like the biggest outage that we have on our infrastructure. We fully recovered, but since then we are working on trying to implement business continuity strategies, and for RBDs specifically, the plan was to spread RBDs over multiple independent clusters. So back in the days, we had one RBD cluster. Now we have 5 RBD clusters. We expose this through OpenStack. They provide different volume types with different QoSs. We have like standard and IO1 general purpose volumes, which are on the HD clusters. We have IO1, IO2, and IO3 on full-fledged storage, and we have also some critical power volumes. These are fully hosted on one special region of our computing center, where the power feeds are actually backed by diesel generators so that everything can stay up and running in the event of a prolonged power outage. So scaling from 1 to 5 clusters in Ceph is not that hard. You basically have to buy the hardware that you need, and then you bootstrap your clusters and you configure them, and everything is up and running. What is a bit more challenging is how to expose these storage options to your users. And for our use case, how to expose those through the OpenStack interface. Initially, we thought of combining the QoS and the physical location of the cluster in the volume type name. This was a very bad idea because it led to the proliferation of volume types, and users had absolutely no idea what to do. It was unclear to them what was the quality of service being delivered and what they would actually need to pick. So we decided to consolidate on QoS, and we have introduced what we call internally the storage availability zones. So availability zones are quite common for what concerns compute. In OpenStack, you have this concept of availability zone. We have basically transposed the same concept onto storage, and currently we operate three clusters for standard and IO1s, which constitute 3 different availability zones. They have different UPSs, different power. They are on different network branches so that we minimize the likelihood that 2 of those go down at the same time. And users that run applications on top of that, if they know what they are doing and they run storage-aware applications, they can actually go and pick different backends to deploy their application in the best possible way. Now, let's transition from business continuity to disaster recovery. We're looking into 2 features for disaster recovery. The first one is Ceph RBD Mirroring. This is actually a bit hybrid between BC and DR. It's actually providing you the way to achieve an active-passive setup, so it works a bit in both contexts. And the second topic we're going through is OpenStack Cinder backup drivers. This is the more traditional backup and restore approach. So for what concerns RBD mirroring, there are two ways you can do RBD mirroring. The first one is with RBD journals. The second is with RBD snapshots. We started with journals because it's fully supported by OpenStack out of the box, but this has severe performance implication on the RBD clients. They are basically subject now to do double writes into the main active RBD image and also into the journal. So in this plot here, you can see the bandwidth and the number of operations that you get out of the cluster with no journal in blue and journals on HDDs or SSDs. So in the case of journal on HDDs, the cluster turns out to be almost unusable. But even in the case of SSDs, for big 4 meg writes, you can get basically 50% out of your clusters with respect to you not using any journaling. So this is pretty bad. We didn't want to expose all this complexity to the clients, and so we switched to the snapshot-based mirroring. This is much more efficient. The clients are not exposed to the complexity of the mirroring. Everything stays in the backend. It scales very well. The performance are also pretty good. And the impact that you have is basically related only to the snapshot trimming and to the replay workload. Now, one thing which is a sort of a limitation for us in deploying this feature is that we were considering pool-based snapshotting and mirroring, which means if you have to fail over, you fail over the whole pool, which at CERN means typically one full cluster and petabytes of data. So it's not that easy to take the decision and say, okay, I'm pushing the button and I'm failing over. It comes with some complexity from the compute layer, so it's not something that you do with a light heart. And also, it's something that the users definitely do not control, so for them it's not a feature that could be helpful in a more traditional rollback or restore for rollback and restore needs. For actually rollback and restore needs, we have investigated a bit the OpenStack Cinder drivers. They support different backends. The one we have investigated are the ones talking to S3 and talking to Ceph RBD. We have started with the S3 driver, so using S3 as a backup target because we already use S3 for many other backup use cases. And we are looking into some advanced S3 features, Abhi, we will talk about, that could help us in migrating things around and maybe even using external S3 endpoints. The problem of this driver is that the implementation is quite inefficient. It doesn't scale so well with the size of the image. As you can see here, it basically takes 7-8 minutes to do the backup of a 5 gigs image, which it's just too slow for our use case. The typical ballpark of RBD images that we handle is tens or hundreds of gigabytes, maybe even terabytes, so it's pretty much slow. You can tune some parameters, chunk size, compression algorithm, but none of these is actually a game changer. And the support for incremental backups is pretty poor. What actually works extremely well is the backup driver that uses another RBD cluster as a destination. If you look what happens under the hood, the driver itself uses librd, and you're basically flying the bytes over from the source to the target cluster by doing export diff and import diff on the source and the destination respectively. So you can actually access all the low-level RBD features which are making this thing very, very efficient. The performance are good out of the box. They scale very nicely with the number of concurrent backups that you do at the same time. And the time it takes to make the backup is actually proportional to the size of the image that you want to backup. So there is no degradation there. Incremental backups are also quite efficient because, again, it uses librd. So if the cluster supports advanced RBD features like fastdiff and object map, you can just fly the thin layer that contains the extents that were changed from the previous backup that you took. And this is all quite effective, as you can see from the plot. The time it takes is not directly proportional to the amount of changes that you apply into the RBD image, but there is clearly a trend, and the trend is consistent. So to summarize about RBD, we are trying to achieve business continuity by spreading the RBD images over multiple clusters, providing more or less the same QoS. This requires coordination with the users. We have consolidated our RBD clusters into different storage availabilities, and it was actually pretty practical to do. It's now clear to users what is the slow storage and the fast storage. For what concerns disaster recovery features, RBD mirroring provided by Ceph is very good if your plan is to fail over an entire cluster or an entire pool or an entire image. If you go down to the image granularity, please use the one based on snapshots, because otherwise clients will be extremely busy in doing double writes. And also the backup drivers from OpenStack Cinder are quite good when they go down to the low-level RBD features that Ceph implements. And this is actually something that you can, again, expose to the users if you have OpenStack and make a self-service feature out of it. So I now transition into object storage and then leave the floor to Abhi. So object storage at CERN is primarily two clusters. These two clusters are fully independent, one from the other. At the moment, we are testing a lot with Multisite, but as of today, they just run in two very independent and simple configurations, one zone group, one zone each. They don't talk to each other. The main cluster uses 4+2 erasure coding for the data. Clearly, the bucket indices are replicated. We use Traffic as a front end. I don't know how many of you are familiar with it. It's pretty much similar to what HA proxy does. It does nice things for us. It does TLS termination. It does regular health checks against the Rados gateways in case something is failing. And what we also do is that we apply some pattern matching on the bucket names, and we have a sort of level 7 routing thing to isolate the traffic of some special customers or noisy neighbors so that they do not impact the general service when they put too much load on the Ceph object storage. The second cluster, again, it's fully independent for now. I think this is actually the biggest cluster that we're operating at the moment, 25 petabytes in size and roughly 2,000 OSDs. And we use it mostly for backups. So yesterday there was a very interesting presentation by Bloomberg about S3 Multisite. We have looked into S3 Multisite quite a lot. I will talk about the traditional simple multi-site setup, which means you have two clusters and a full replication across the two zones. You have a master zone, you have a secondary zone. They are both read-writes, and they sync everything, every single object, through dedicated Rados gateways that we have configured as the zone endpoints. We ran some tests with Warp, the Mini.io Warp tooling. This is not specific to multi-site deployments, but it's very practical if you just want to put some load against your S3 clusters. We have identified some pain points. Our observations pretty much match what Bloomberg was presenting yesterday. We have some further comments. Sync may lag behind in some cases. We have deliberately decided to kill the secondary zone one day and put 1 million objects on the primary zone, and it actually took a very long time to sync back. We were waiting for 1 day for the two clusters to be back in sync, and this is a bit too long if you're using this for production and serious disaster recovery use cases. Bucket index resharding is still quite a thing. It can be stressful if you have to do it on a production cluster. You can easily reshard on the master zone. The secondary zone doesn't fully completely, so you have complete the resharding, so you have to babysit the process and apply some gentle kicks here and there. So I'm not completely sure we would be able or be happy to do that in a production cluster. And another problem that we have identified is that there is an intrinsic replication delay between the master zone and the secondary zone. This is basically because S3 internally does multisite as a queue, so the secondary site has to replay and pull the objects which are missing. The replication delay is not that small. We are here measuring the replication on put and on delete. It can go high to 15 seconds, and also the jitter is pretty much high. So for us, the problem of how to expose a multi-site to clients, it remains. If you want to expose one single endpoint, you have to apply some ingenuity on behind the scenes to make sure that the clients are actually having a consistent view on the objects that are uploaded. This is just a very short digression about BGP load balancing. At the moment, we are using this only for a test cluster. Production is on traditional DNS-based round robin. BGP-based basically means that you have two sets of load balancers, one at the TCP level that directly talks to the network routers, and then you have a second layer, the traditional traffic plus Rados gateway, or HA proxy plus Rados gateway. It's very practical because you expose one virtual IP to the clients, but at the very same time, it doesn't completely fix the problem of the multi-site replication. So it's something that you would use to replace more traditional ways to do load balancing, but still the multi-site specific things should be solved in some other way. So Abhi, floor is yours.
So continuing on the multi-site strategy, we also started evaluating more multi-site options. So one thing with Quincy Plus you get is like something called sync policies. And this is basically allowing for more fine-grained control, where you would actually allow certain policies at a zone group level and then enable them at a per bucket level. So it's more user control replication. So user can particularly replicate the bucket that they feel important with something called S3 put bucket replication API. And we did test this, and we found certain issues with this in the sense we tested this on Quincy without the fixes that were discussed yesterday. So when we enabled symmetric flow with zones, what we did observe is that if there is a bucket that is actually replicating on two zones, if there is some data, the global sync status of the site itself says it's okay. Whereas if you go for a per bucket statistics, it says that it's not replicated. And the only way sometimes you can force a recovery is by using a hammer kind of thing, where you actually disable and enable the sync as an admin on the particular bucket. And this always seems to work, but this is not something that you would want to do in a production site. And we also noticed that if you actually enable this API after some objects already are present in the secondary zone, then the objects almost never sync back, other than if you do a master zone failover, which is not really practical. And moving on to other strategies for doing the same thing, we started looking into cloud sync. The idea would be one that you can sync to external clouds which offer an S3-like API. The other option is that we don't need to, for sites which are disconnected already, we could potentially use this as a methodology to actually sync specific buckets without paying for the cost of an entire zone replication, since it's a bit non-intrusive. And as far as configuration goes, it's relatively simple. You just require a particular storage class on a particular zone, which you configure lifecycle policies to. And the lifecycle policies essentially configure something like, transition after 7 days or something like this. And this would move to the next tier, which would be an external cloud. Currently, in the current implementation of Rados Gateway, there's actually a single site for the remote site, but there might be future improvements in this particular area. And a potential future implementation that requires some development would be like potentially use this as a methodology to transition to something like Amazon Glacier or something like a tape REST API. One another possibility in this particular cloud sync domain is something called as a cloud sync module. But this seems to be a mirror zone which actually forwards everything to an external cloud. But we have had issues when we tried this. And we're not sure whether this is a maintained version over the Cloud Sync lifecycle policy, which seems to be more well-maintained and robust. Moving on to the whole story of disaster recovery itself, we do also have multiple other options to actually make sure that the objects do not get deleted. One classical way in S3 is using versioning. And then there are 3 or 4 other methodologies which are built on top of versioning with object locks and legal holes and these sort of things, which essentially prevent, for example, a user to make a mistake where they actually accidentally overwrite an object which they're not supposed to, or enforce site-like policies and these sort of things. One potentially interesting thing that we evaluated on this regard is the archive zone. And the idea is basically that you would have multiple zones where you would want to preserve all the archived versions of the same object. And the archive zone potentially does this. And it seems to be intelligent enough to understand if the bucket on a local zone is actually versioned. So it doesn't do write amplification as far as the object is already versioned. Obviously, with multisite, it also comes with the eventual consistency caveat. So what we did observe is that we have potential seconds of latency between 2 sites, even though they have a pretty close location. So if you actually do a write and a delete in a succession, then of course this object will not be mirrored in the correct time for the archive zone to catch up. Also, one other interesting quirk we noticed is that if you have multiple zones that actually try to archive to a particular zone, we would end up the intrinsic replication of multisite and the archive zone replication, which would end up with double copies of the object or n copies depending on the n number of sites you have, which is something that potentially needs fixing. Moving on, so this basically summarizes the whole S3 story we have. We found that like classical S3 is pretty reliable and it works beautifully with L7 routing as well. Immutable backups, they pretty much work very well with object versioning, and you have fine-grained control with locks and many of these sort of possibilities. Traditional multi-site, you get simple all or nothing affair. It kind of works, but there are some issues like what was being discussed yesterday, but we have fixes in the future, so we expect more future fixes in this particular domain. And fine-grained sync policies in Quincy, they're already present, but I would imagine they would be stabilized more in Reef and further, and this would be something nice to have, where you could have more fine-grained control with user domain replication. Moving on to the last protocol we have, it's the file system. Similar to the RBD story, Ceph file system at CERN, we started as a single file system. We have 8 MDSs, 4 active and 4 standby. It's potentially for, it started as OpenStack Manila, and then we have some HPC use cases on it. The metadata pools themselves live on SSDs. And as far as snapshotting and everything is concerned, we don't have any snapshots on this particular cluster. And this cluster existed before ephemeral pinning existed, so we do have a script that essentially does pinning onto particular MDSs on a hash-based algorithm. But we are evaluating ephemeral pinning, and we might enable that as a future option. Similar to the whole business continuity story, we eventually sharded out into multiple CephFS clusters, depending on the use case. So we have an all-flash cluster. We have 2 general-purpose CephFS cluster. We have 1 dedicated to open search use cases and 1 hyperconverged cluster that is co-located with compute. We also very recently moved one of the entire Ceph clusters, which is which was split across the data center into the power critical area. This was an all-flash cluster. I'll not cover this right now because we might be running out of time, but we do have this in the additional slides, so if we have extra time, we can cover this. This was pretty much achieved with zero downtime with easy crush rules that we already support in Ceph, but there's nothing CephFS specific. One thing as far as the disaster recovery story is concerned is CephFS Snapshots, and we started evaluating this for our use cases. And as far as configuring snapshots itself is concerned, it is a very simple configuration where you set up a particular flag on an MDS called allow new slaps. And this is default since Quincy Plus. However, if you do configure this flag at this current point in time, as far as the UX goes, there isn't any option that actually shows that this flag is enabled. It's kind of disappeared it's not in the Mon store like other configuration options are. So this is something we might potentially need to fix. And as far as snapshots themselves go, as far as a client is concerned, it's actually a simple .snap directory that is actually hidden. It's not visible even if you do listing with a all flag or something like this. And as far as a user is concerned, the operation of creating a snapshot is simply creating a folder in this particular directory that would essentially do copy and write snapshots. And with copy and write, of course, like some things like deletes and these sort of things would be the one that would be affected. And other than this possibility, as an administrator, you also have other possibilities with respect to sub-volume snapshots. This is where you can actually create a sub-volume snapshot as an administrator, and that would do the same thing. So when we started evaluating this, we started with a very simple workload where we have a deep hierarchical tree and something as simple as like, untarring and removing directory trees. We didn't do snapshotting in between the operations, but it was just a directory which had snapshots previously enabled. And we did see that there was a noticeable performance hit when you started enabling snapshots in removal workloads. And analyzing further onto the MDSs themselves, we do see that it was potentially in one particular thread that always saw this particular CPU bump, and this was essentially the finisher thread. And this was taking like 30 to 40% of the CPU times from more than usual. And we're looking at upstream, we do see a very well described issue called by Andreas Pataki. And this was essentially, confirming the same things that was actually in the issue. That is like when you do snapshots, there are certain structures that keep track of caps and these sort of things, and these seem to be heavily loaded. There are potential fixes being discussed, but these are not in the main branch just yet. But this would be something that we'd expect in the future. So, as of now, what we have understood is that potentially the problems that we see with snapshots are localized to the MDS daemon. So we could, in theory, actually roll out this feature by pinning particular workloads with snapshots onto particular MDSs so that other MDSs don't see the same load. This is something that we have to evaluate, but this is something we are planning to do. Because we want this particular use case that, people doing CI-like or analytics sort of workloads do not actually pay the cost for snapshots, whereas like potential workflows which require snapshots pay that particular cost. Of course, this solution does not work if everybody requires snapshots. So this is something that we would expect the main branch fix to land at some point and, come back to this. And other than this, for the backup story, the another thing what we already have at CERN is something called cback, which is potentially something that we use for backing up any kind of shared file system we have. We have another file system at CERN for physics data use cases called EOS, and other than CephFS. And we orchestrate backups using RESTEC. This is potentially an architecture we have. It basically has different queues for tracking various states. And we essentially just back it up using RESTEC to our S3 cluster. We have close to a petabyte, 850 million files backed up every day, and almost 6 petabytes of backups in S3 using RESTEC. It works pretty well for our use cases. One potential thing that we are evaluating for the future is also expanding this particular tool for doing backups to tape. So RESTEC, as of currently, requires like backups. RESTEC stores backups of both metadata and data packed together. Of course, this wouldn't fly in the tape scenario. So the architecture evolves around the point that we have a slower media, so we should actually potentially store metadata elsewhere. And this is a potential architecture we are currently working on to do backups to tape. And we are trying to optimize write paths on this particular use case. And this should pretty much cover our backup use cases. I'll leave the conclusions back to Enrico.
Yep. So I promise I will be super short here. So for what concerns business continuity, it is somehow achievable, okay? The golden rule is do not put all your eggs into the same basket. If you run Ceph at a given capacity and scale, just spread things over different clusters. There are relevant replication features like RBD Mirroring and S3 Multisite that can help you in some sort of active-passive setups. CephFS Snapshots and Mirroring, it's not completely there yet, but we're looking forward to test this more. What is also essential to achieve business continuity is to coordinate with the layers, if you have any, that stands above you to deliver the infrastructure as a service, and also talk to your users so that power users know what is your storage offer and how to make the best use out of it. Now, for business continuity, you may be surprised by the fact that we didn't mention stretch clusters. We are doing it now. The perfect deployment case for stretch clusters is you have 2 data centers. We do not have 2 data centers at the moment. We will have a second one soon. So it's something that we are evaluating and we are considering. But due to the OpenStack integration that we have, it's a bit complicated to orchestrate the whole thing end to end, like respawning VMs on the data center that didn't fail and reattach the RBD volumes is not completely straightforward. For CephFS is actually easier to do. We will see if this is really the thing we want to deploy in prod. For disaster recovery, this for us mainly means backup and restore from the backup in case of a disaster. You have seen for sure that we jumped straight into specific things that we may want to implement for blocks, for files, and for objects. You have the whole breakdown here. I'm not going into anything more detailed than this. We just wonder if there is like a more low-level general disaster recovery feature for Ceph. We may look into the logical volumes on which the OSDs run. And tape is definitely one thing we are pretty much interested into. There were several discussions about tapes. So if you're also looking into tapes for your backup needs, please come and talk to us. We are very much interested. So that's it. If there are any questions, we're happy to take those. We don't see any of you.
Sorry, we can't see.
With so many clusters, how you deal with automation, configuration management, and so on? Sorry for the long question. Maybe.
No. We run everything in bare metal. We use Puppet as a configuration manager. I do not think we do much of automation for the time being. We have like a layer of custom scripts that make sure that the configuration parameters that are relevant for us are actually enforced on every single cluster. But when we want to do upgrades, we typically do that in a sort of manual fashion. This is not something that we do very frequently. I think we would like upgrade our clusters a couple of times, 3 times a year, at least for what concerns the serious production clusters. And they are all typically deployed in a way that we can upgrade the Ceph packages on one entire rack and restart all the daemons on one entire rack. So the procedure itself, it doesn't take a lot of time. Thanks, Abhi.
When you recover from backup, what's your RPU and RTU time?
This is something we are still testing because it basically depends on the load and it depends on the amount of things which are failing at the same time and therefore the load that you put on the restore side. We're looking forward into it. I do not think we have any stable number that we can present at the moment. But the thing that we want to achieve is to have something that scales pretty well in terms of number of concurrent restores that you can have. And then clearly you will maybe hit some bottlenecks in terms of what a cluster can deliver and what the network can deliver. The restore in our use case would anyway be in a different cluster, which is not the cluster where the backup is stored. So there is some network overhead to be measured.
So you said that restore might need some more work.
Yep.
If there is some disaster, have you hit any disaster or worked with recovery scenario itself? And how was the application affected during that time? Was it a smooth transition or did you, how would you react to such scenario?
We are trying to come up with a policy, which is actually a policy and a strategy with the whole IT department. We're basically just doing Ceph. Okay, when you have other teams which are doing OpenStack, and then we have other teams which are taking care of the fabric of the network, all the rest, and more application exposed service teams. We are trying to come up with clear procedures how to orchestrate all of this across the department. Fortunately, we cannot learn from experience yet.
Also, with respect to restores, it's also the application people that can understand whether the application is in a consistent state. We, as a storage provider, cannot completely know. I mean, we can only know that it was a consistent state of backup that we recovered from, but the application has to understand, what state it is in to recover.
Two questions. The first one is about this cback tool. Why you wrote that? What does more than the typical common S3 client you could use to?
You want to? Should I take it? So we are basically, there you go. We're backing up. We have 40,000 backup jobs a day that run on a daily basis. So this is the logic of the backup itself is basically restic. There is nothing special into it. We just deployed it and made it such that there is a centralized database where we keep track of the backups which are waiting, running, or completed. And then we have agents which are basically workers, and they take on some of this work and they run the backup jobs. It's the scale that changes.
Okay, thank you. And the second one is you have many clusters. Do you always dedicate servers to monitors and other gateway?
In the past, the mons were running on VMs. Now we try. We collocate those on the same bare metal nodes where we also have the OSDs, so disk servers. Also because the resources that you need are not high. We always have enough CPU and memory on these nodes, so there is no actual need to reserve additional hardware or additional VMs to run the control plane, to run the mons and the MGRs. For the MDSs, we have dedicated machines because typically there you need, at least for our use cases, you need quite some memory. The RGWs we have a mixed configuration. We can run those on VMs and on bare metal, but the memory requirements are not so high. So we have more flexibility there for the deployment. We run many active Rados gateways at the same time. I think the main production cluster is actually 16 Rados gateways, and we have this mechanism to cluster requests. So we basically achieve throughput and concurrency, but by just running more, let's say, a higher number of smaller Rados gateways altogether.
Did you try to the setup of the Rados gateways? Did you try to split them into groups and give them different jobs? That is, for example, say, okay, I disabled garbage collection of all of them. I just gave garbage collection to a specific group that is not customer facing.
Not yet. We know there were some problems around this in the past. Someone was suffering from the fact that there were like heavy deletes on the clusters, and this was actually impacting the performance of Rados gateways, also serving the client requests. We didn't hit that. It would be very easy for us to spawn some additional Rados gateways which are not exposed to client traffic and just take care of deletions or garbage collection or lifecycle policies, etc.
I mean, the basic question behind this, I'm not a great fan that the multi-site is inside of the Rados gateway itself.
Okay.
So the question is how we can mitigate this, that we perhaps say, okay, sometimes we just move out of the client traffic and just give them enough resources.
So if you're talking explicitly about the sync traffic between the two sites, you can actually configure that. You can have dedicated Rados gateways which are just responsible for the sync, and none of those will actually talk to the clients. And we are actually doing that. at the moment. Okay. Enjoy lunch. Thanks a lot.